Okay, I want to derive the kinematic equations for constant acceleration, and I'm going to do that with a combination of graphical reasoning and algebra reasoning. I'm going to start with acceleration. You should know what that means, and here is an A versus T plot. Horizontal is time, and the vertical is acceleration, and the units are meters per second squared. And I'm going to assume a constant value for acceleration. So acceleration as a function of time is equal to a naught. I'm going to assume a horizontal motion. Motion is occurring in horizontal direction, and so I should, technically speaking, I should add a little x subscript here and here. And so if I'm accelerating in the x direction, I have a positive acceleration. It means my acceleration, my velocity is increasing towards the right. Okay, so the next quantity to discuss is velocity. Here is the velocity versus time. Units are meters per second. I'm going to assume at time 0 I have some velocity v naught. Doesn't have to be a positive velocity. It's shown as a positive velocity here because it's above the x-axis. But I'm going to start with some velocity, not necessarily 0. And that now is going to increase according to this equation, v naught plus a naught t. The slope of this is that. And so I've color-coded this to remind you that this is a y equals mx plus b type of equation, and the multiplier for t, it's actually varies as a function of t, not x, is the slope, and that comes from here. So velocity, the way I've sketched it here with the positive acceleration, is has a positive straight line and it's increasing. Okay, so the next thing to talk about is position, and again I'm going to assume some kind of a starting position, not necessarily 0. X naught is what I'm going to use here. So the x position is going to be, x displacement is going to be the initial x position plus the average value from 0 to t, which is the starting velocity, that's this guy, plus the ending velocity, which is this guy. So that's going to be v naught plus v of t over 2 times t. I can do that because the velocity is a straight line. If it wasn't a straight line, I could not do that. So that plugging v of t in for v of t here, that becomes x naught plus v naught plus a naught t, all divided by 2 times t, and that simplifies to x of t equals x naught plus v naught t plus 1/2 a naught t squared. So this is equation 1, equation 2, equation 3. Equation 4, which I implicitly use to get equation 3, is if you just want to think about average velocity, the displacement, the position as a function of t is equal to the initial position plus the average velocity from 0 to t times the time period. That's equation number 4. Okay, the last thing you can do here is you can eliminate between equations 2 and 3, you can eliminate time. There's some algebra involved there. Essentially what one does is one solves this equation for t and then plugs that into this equation. So you eliminate t, and then what you end up with is this equation 5 down here. V squared, so in other words that's at time t, it's some later time, that's supposed to be a t there, squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. X minus x naught is going to be the displacement of the particle. So this is a very useful equation here. It's essentially conservation of energy, and there's no time involved. So if you find yourself having to solve things in terms in a situation where you don't know what time is, this is the equation that one usually uses.